Hey everyone, so today we're going to be going over how to do some rotational equilibrium problems. Right? But before that, let's just get a quick background on what it means for an object to be in rotational equilibrium and some tips we're going to need to be able to do all of these problems. So the definition of rotational equilibrium is that the net torque on an object equals zero. Okay? Now, how do we get a net torque to equal zero? Right? Well, for torques, we have two main directions. We've got torque counterclockwise and torque clockwise. Okay? When setting up a net torque equation, we need to understand which forces are causing a torque in either of these directions. Since they are opposite directions, that means we throw a negative sign in there. And since we're dealing with equilibrium, again, that net torque equals zero. Okay? So, since we have torque counterclockwise minus torque clockwise equaling zero, I can add over torque clockwise, and we end up with torque counterclockwise equals torque clockwise. Okay? And it's right here, this piece right here, the torque counterclockwise equals torque clockwise, is how we're going to start all of our problems. Okay? Now, once again, before we get started, there's just a little bit more I want to go through, and these are these quick little tips and reminders that you want to tell yourself before you start any problem. Okay, there's three quick ones. Right? So the first one has to do with the moment arm. Okay, the moment arm. So remember, the moment arm is defined as the distance from where that force is applied to the pivot point. Okay, that's important. You'll want to measure that distance. It's a straight line distance. Okay, and any angle in between the force and that moment arm goes in that sine theta, which we'll get to a little bit. Okay, so that's our moment arm. Now, the next thing is the pivot point. Okay, the pivot point. You choose for any problem where that pivot point is. Okay, some spots, some problems, it'll be obvious. Like if you have a meter stick or a beam or something like that that's on a fulcrum, that's very obvious, right? It's going to rotate about that fulcrum. Other systems, which we're going to get to in these problems, not as obvious, but I'll give you the tip to pick the one that'll make your life the easiest. Okay? And the third one has to do with the weight on the beam. Now you'll hear me throughout this video kind of interchanging beam or stick. It doesn't matter. It just defines or represents an object that is not like localized at a point. Okay? So it's like a beam or a stick rather than, say, a ball or a mass or something like that. Okay? The weight of the beam, we always say, is localized at the center of mass. Okay? It doesn't matter if it's a uniform system or not. We're usually going to have uniform since it's easier to work with, but it doesn't matter. Any object that you ever deal with in your whole life, you say that the mass is localized at that center of mass, and that's where gravity acts. Okay? And it acts on that center of mass, which is where we say that's where the force is applied. Great. So let's set up our first problem of three, and we will go through it. So the first one we're going to make pretty simple. It's going to be a stick on a fulcrum. So let me draw the main system. So here we go. Here is our stick. Here's our fulcrum. What I did was I made this fulcrum just a little bit off-center. Now, obviously, it doesn't matter if it's off-center to the left or off-center to the right. Just make sure that you follow through properly. Okay. Now, I'm going to get some numbers on here, and we're going to go. So, what I'm also going to do is have a mass hanging from the way end of the stick on the shorter end of the stick. Okay, so we have our fulcrum. Here's our whole stick. Here's a mass hanging here. And this is most of the stick. We're going to say that from the mass to the pivot point, to that fulcrum, is 0.75 meters. Okay? I'm going to give you a few more numbers, and we're going to use that space over here to calculate what we're going to end up being asked to find. So we're going to say that the length of the entire beam is 2.5 meters. Okay? So from this end all the way to this end is 2.5 meters. Okay? The mass that is hanging over here, okay, we're going to say is 400 grams. Okay, we know this distance here, but what are we going to be looking for? Well, we're going to look for the mass of the beam. Okay, so how heavy or what is the mass of this beam? Okay. Well, this is a rotational equilibrium problem. Like I said before, we're going to start with torque counterclockwise equals torque clockwise. So let's go through and see how to set up each of these problems. Well, what force or forces would cause this system here to rotate counterclockwise? Well, it's going to be this guy right here. Okay? If this stick didn't have any mass, this force here would cause this whole thing to rotate that way, counterclockwise. So we're going to say it's the force of this mass acting from that pivot point over. So equation for torque is force times the moment arm times sine theta. Okay? How about clockwise? Well, if we didn't have this mass and we just had the stick on the fulcrum, it would be just the mass of the meter stick, right? There's no other object here. So it's just the mass of the meter stick acting at its center of mass that would pull it down, that would cause this whole system to rotate this way. Okay, so we'll write that down. F R sine theta. Great. Now, let's go through what each of these symbols mean. We'll be able to plug stuff in. Great, great, great. Now, first, what force is it for either of these two things, either the stick or the mass, that's causing the torque? Well, in this case, it's gravity, right? It's the weight of this mass, it's the weight of this stick. So we can rewrite those as that. So Fg, R. Now, the theta, we'll get back to the moment arm in a second, but the theta, what's the theta? Remember, that is the force between where the force is applied from the pivot point, so that's that moment arm, and the amount of force that's there. Since the force is down and the moment arm is horizontal, our angle is 90 degrees. Sine of 90 degrees is just 1. So I'm going to leave that blank. Whoop. There we go. On this side, again, it's the weight of the stick that's pulling it down there. Force of gravity times that moment arm. Again, our theta is 90. The force here is down. The moment arm is horizontal. Let's plug stuff in. All right. Well, how do we find force of gravity? That F sub g. Well, that's mass times acceleration due to gravity. M times g times your moment arm. M times g times your moment arm. Okay. Mass times acceleration due to gravity is your weight. Mass times acceleration due to gravity is your weight. Now, one quick thing, just because I'm not really notating it here, remember these are different masses, these are different moment arms, so we can't cancel those out, but this is the same acceleration due to gravity. We are on the same planet, whatever happens to be. Okay? You can't have half the stick on one planet and have it say, oh, it's different. Anywho, so let's go through. We know this mass, that's the mass here, this 400 grams. We know this moment arm, that's 0.75, right? Because the force is here, the moment arm, or the pivot point's here, that moment arm is at 0.75. So let's write that down. 400 grams is 0.4 kilograms times our moment arm, which is 0.75 meters. Okay, there we go. Now, we're looking for the mass of the stick, so that's our unknown mass. Okay. And now we need to figure out what is going to be our moment arm. So again, I'm going to say this a bunch throughout this whole video. The moment arm is from where the force is applied to the pivot point. We're talking about the stick or the beam. That force is always applied from the center of mass. Okay, so that would be here. Well, how can we figure out then what here is to here? Okay, well, we know the whole length from here to here is 2.5 meters, which means half of it, 1.25. Right? So if I know from here to the end is 1.25, and I know that this bit, from this mass, from this end to the pivot point is 0.75, well, then I'll do 1.25 minus 0.75, which leaves just 0.5, a half a meter. 0.5 meters. Okay, so now here's our plugged in values, right? Of course, we have our equations, substitution with units. And now we're just going to plug this into our calculator, 0.4 kilograms times 0.75 meters, divided by 0.5 meters, and we end up with, ta-da, 0.6 kilograms. Okay, awesome. Pretty simple. You know, it can get a little bit more complicated depending on the problem that they give you. They could add another mass over here, another mass over here, or change different things up, give you the numbers in a different way. As long as you have one torque term, so FR sine theta for each object, the mass, the stick, any other masses, and you set them up properly so that all of them that cause counterclockwise are on one side and all that cause clockwise are on the other side, you're good to go. Just make sure you keep track of each object and which side of the equal sign it goes. Okay? All right, so there you go. Now, let's set up the next problem. In this scenario, we're going to have an object that's going to kind of look like this. I've got a nice paint stir stick here. So let's pretend this is our wall. We're going to have a beam coming off of that wall. And from the end of the beam or somewhere on the beam, there'll be a sign. And there's going to be a cable kind of supporting the beam. So let's draw a picture of that. Okay. So here we have our wall. And there's a beam. I feel like Bob Ross a little bit here. Okay. And then a mass hanging off the end, in this case, and there is a cable supporting the whole system. Okay, so here's our wall. You just draw, that's a generic physics type of notation for a wall or ceiling or something, just a line with the little dashes. Here's our beam. Here is a mass hanging off the end of that beam. And here is a cable that is supporting that whole system at some angle. All right, so let's get some numbers through and let's figure out what we got to figure out. All right, so we're going to say that theta, in this case, is 22 degrees. Make sure your calculator is in degree mode. Okay, we're going to say the mass of the beam is 75 kilograms. And we're going to say that the mass of the sign is 15 kilograms. And we're going to look for the tension in the cable. Okay, so we're going to look at what force that this cable is pulling back up. Now, earlier in the video, you heard me say that sometimes you got to pick where you want your pivot point to be. This is one of those scenarios. Okay, there's no obvious spot like there would be with a fulcrum or something. Okay, I strongly suggest making this point right here, where the beam meets the wall, to be your focal point. Okay? You could pick here or here or here, or in the middle of the beam or wherever, but it will make your job more difficult. Right here, we have a surface contact point. The beam is in contact with the wall. What happens when you have two objects in contact with one another? Well, you get a normal force. So that normal force would act as a torque force. That makes it very complicated since you need to have a horizontal component so it doesn't smush into the wall this way, and a vertical component so it doesn't slip down. Makes it a bit complicated. By choosing your pivot point to be right here where the beam meets the wall, you don't need to take those into account, right? Because then your moment arm is 0. It doesn't affect your torques. So if we say this is our moment arm, or sorry, our pivot point, we can do all of our calculations based off of this point here. Great. Let's do it. Okay, so again, we start torque counterclockwise equals torque clockwise. All rotational equilibrium problems will start with this setup. All right, so let's take a look. What forces might cause this system to rotate counterclockwise? Well, let's take a look. We've got this mass here that's pulling down. That would cause this to rotate this way. Okay, and that appears to be clockwise. We've got the weight of the beam. Again, this is our pivot point. That would pull down that way. Okay, that's clockwise. We've got our cable. Well, the cable would pull up this way. Oh, there's our counterclockwise. All right, so torque equals force times the moment arm times sine theta. Okay. I already established that this is our force of tension. That way I don't need to waste a spot there, but that is our tension force that we're going to end up solving for. Here's our moment arm, and here's our sine, and there's our theta. This theta is going to be important because if my tension's up this way, here's my force. My moment arm is this way. That angle has to go there. All right, now clockwise. Well, we already established this force from this mass and this force from the beam would cause clockwise. Just like in the previous problem, those angles are 90 degrees. So just in the sake of saving space, I'm going to skip writing the sine theta. So we have the force of gravity from the sine times that moment arm plus the force of gravity from the beam times that moment arm. Okay, so here's our setup. Force of tension times the moment arm of the cable times the sine of the angle between the cable and the beam equal the force of gravity from the sine times that moment arm plus the force of gravity of the beam times that moment arm. Great. Now, one thing I want to say before we continue is, in the previous problem, we were able to cancel out accelerations due to gravity. We can't do that this time because there's no acceleration due to gravity in this term that we're going to be able to get rid of. Okay, if we were to do that, we'd have to divide this whole side by 9.81. But since we're solving for t, we'd have to multiply it through anyways. But let's just not worry about it. Let's just multiply it through right here. So let's plug some stuff in. All right, force of tension, cool, that's our unknown, times the moment arm. Interesting. I didn't give a length. So how can I calculate or write down a moment arm if I didn't give a length? Well, let's get back into it. For now, I'll just supplement an L for length, the length of the beam in for that moment arm, right? Because the pivot point's here, the cable acts on the end, so that's the entire length of the beam. Okay, times the sine of 22 degrees equals, right? We'll have the force of gravity from the sine, okay, so that is 15 kilograms times 9.81 meters per second squared times, interesting, again, that length, but the sine's here, the pivot point's here, there's an L. I'm going to write that little L there, okay? Ran out of space, so I'm just going to write this a little bit below. Sorry about that. Okay. Now we're going to do the force of gravity from the beam. Okay. Remember, the beam applies its force at the center of mass. So we measure from the pivot point to that center of mass. So we'll say that is our 75 kilograms times 9.81 meters per second squared. But our moment arm now is half of the length. So that's going to be L over 2. L over 2. Okay? So here's our setup. Again, I apologize that it's all kind of in two different lines, but hopefully you get the idea. Force of tension, our unknown, times a still unknown length, times the sine of 22 degrees equals 15 kilograms times 9.81 meters per second squared, times again our unknown moment arm, which is just the length of the beam, plus 75 kilograms times 9.81 meters per second squared times L over 2. Okay, cool. Remember how we didn't have that moment arm, the length of the beam? Well, guess what? We have an L here, we have an L here, and we have an L over 2 here, but there's an L, so I can cancel out an L in each spot, so that ends up just being essentially 75 kilograms times 9.81, all divided by 2. Okay, because you're multiplying by 1 over 2, it's just multiplying by half. All right, so let's simplify so we get a little bit more space to work with. So we'll write force times tension, or force of tension, times the sine of 22 degrees equals, and then that first term is that 15 times 9.81 is 147.12. That ends up being newtons. Plus, the other bit is 367.875 newtons. Okay. I apologize, I'm kind of squished over here, but that is 147.12 newtons plus 367.875 newtons. Okay. Add up, divide by the sine of 22 degrees. Again, make sure your calculator is in degree mode, and you get a tension of 1,374.8 newtons. Ta-da! Okay, so we have this added bit where we have to pick our pivot point. We have this whole cable at an angle, but really it's no different than the problem we did before. We set up our torques counterclockwise, our torques clockwise, and we just kind of go from there. Awesome. Great. So that is that one. Now we've got one more type of problemo that we want to get through. Okay. And this one is just kind of adding just a little bit more to that problem we just did. But also kind of taking something away, you'll see. Anywho, what we're going to have is a beam that is supported by a chain on either end. Okay? We're supported by a chain on either end. So it's kind of like hanging from a ceiling, something like this. All right? Now, I'm going to say, just because I feel like it, that there's a rock somewhere, like my little cauliflower-looking rock. Okay? There's a rock somewhere here on the platform, whatever that happens to be. Okay? Let's get some numbers, and I'll tell you what I'm looking for in this problem here. All right. So first off, the length of the whole beam is 8 meters for this problem. Okay? I'm going to tell you that the weight of the beam is 20 newtons. Okay. Oops. The weight of the beam is 20 newtons. And the weight of the rock is 55 newtons. Okay. I'm also going to tell you that the force of tension from the right cable, or the right string, whatever happens to be, is also 55 newtons. Okay, so this cable right here has an upward tension of 55 newtons. So to recap, from here to here is 8 meters. The beam itself is 20 newtons. It weighs 20 newtons. This rock that's on top of it is 55 newtons. That's how much it weighs. And this force of tension in this supporting cable on the right side is also 55 newtons. All right? What I want to know, what I'm asking for you here, is how far away from the left cable is this rock? What is the moment arm for this rock? All right then. So let's start from where we always need to start. Torques counterclockwise equal torque clockwise. Cool. Now, in order to get started, we need to be able to choose our pivot point. Since I'm asking you for the distance from the left cable, we'll make that our pivot point. We'll make the left side of the beam our pivot point. That way we don't have to worry about whatever tension is here. All right, let's do it. So, what forces would cause this system to rotate counterclockwise? Okay, well, the rock acts down. That would apply force that way. That's clockwise. The weight of the beam, same thing. This tension in the chain, the right side chain here, whoop, that's our counterclockwise torque. Okay. Now, what's nice is this chain acts up. Our moment arm is horizontal. That angle is 90 degrees. Sine of 90 degrees is 1. So I'm not going to write the sine theta for any of these because, again, the rock is down, horizontal. The beam's down, horizontal. We're good. All right, so counterclockwise torque, that is the force of tension times that moment arm, which is our 8 meters. Well, I'll just write down the R. I'll put in the symbols first. Sorry, equals. Okay, so force of tension times our moment arm, which again is from our pivot point here to all the way over here. Now our clockwise ones. Well, we say that we have this rock. Okay, we don't know where that rock is, so we'll say it's the force of the rock times our unknown moment arm. This is our unknown. Plus, because they're both causing a torque in that same direction, the force of the beam, the weight of that beam. Now again, the beam, its force acts at the center of mass. So that is the moment arm for that. So let's plug some values in. Force of tension. We know that force of tension is 55 meters. And the moment arm for this force of tension over here is the full length of the beam, our 8 meters. 8 meters. Okay. Force of the rock. Okay. We know the weight of the rock, 55 newtons, but we don't know the moment arm for the rock. So 55 newtons times an unknown moment arm, plus the force of the beam, which is the weight of the beam, 20 newtons. Okay. And the moment arm for the beam is at the center of mass. The whole thing is 8. 8 divided by 2, 4. So that's 4 meters. Okay. So let's do a quick calculation here. Okay. 55 times 8 is 190, I believe. I probably got that wrong, but we'll see. No, I got that wrong. You know what? I'm not even going to worry about calculating it through. Apologies. Just do your math. So we have 55 times 8 minus 80 divided by 55. And we get our moment arm to be 6.55 meters. Okay, there we go. There's our answer. Let me circle it. All right. Those are the 3 main types of rotational equilibrium problems that you'll see. So hopefully this helped, and I'll catch you guys next time.